Look, here's what we know. You've got any atom of any of these elements has a nucleus, right? And around that nucleus are electrons. But it's not a solar system view at all. It's not like you have a nucleus, and then in rings, here's an electron and here's an electron. That's not how that looks at all. The electron's not even necessarily a particle. It's got particle properties and it's got wave-like properties. You definitely heard that photons have particle and wave-like properties. When you get really small, particles start behaving like ghosts almost. So an electron is not like one thing. It's almost like a cloud of stuff, which helps us understand what resonance a little bit is about. It's not electrons moving. It's more of like the cloud of electrons spread, right? It's in kind of two places at once, just thinner of a cloud, basically, is what we're talking about. We have to concern ourselves with energy. So if you reach physical chemistry, people have said the class physical chemistry is much harder than orgo. It may be true. I don't know. To me, it was just a different class. So when you get to physical chem, there's something called the particle in the box. And it describes the energy of an electron. And that's what we're trying to show right now. Imagine the middle of this box is a nucleus. Right here, we are looking at a nucleus of an atom. That's obviously positively charged, right? And imagine as we go to the left, we go infinitely away from a nucleus. As we go to the right, we go in another direction infinitely away from the nucleus. Obviously, this is a one-dimensional thing. It's a one-dimensional line. We're not even looking at 2 dimensions or 3-dimensional space, right? So if you want to turn it into, you first learn this, and then you turn it into 3 dimensions. It makes it much more difficult. The x-axis, therefore, is distance from a nucleus. Distance one way or the other way from a nucleus. What is the y-axis? The y-axis here is energy. Now, if you're the electron, where is your lowest energy? Do you remember in Gen Chem there was a formula for lattice energy? Energy is K Q1 Q2 divided by distance. Does anybody remember this formula? Raise your hand if you remember the formula. Okay. Well, how about this? How about this? This comes from something called Coulomb's law, and Coulomb's law, Fc, is equal to K Q1 Q2 over distance squared. We can make sense out of this. The Q in this equation, the Q, is the charge of a particle. So here is the charge of particle 1, and here's the charge of particle 2. Stay with me here. Imagine I had a positive ion and a negative ion, right? They would have some energy of attraction. What do you think would happen if I make this twice as positive and twice as negative? Wouldn't they have a bigger energy of attraction? What if I have them have a particular charge each, but I move one further away? Wouldn't that have less of an attraction? What if I move it closer? Wouldn't that have more of an attraction? And when they attract and collide into each other, they release energy. They go to a lower energy state. And to separate them, think of just a magnet on a fridge. You know, if this magnet is here, it's going to be, and let's say this is a fridge, it's attracted. If there's a much more powerful magnet, it's much more attracted, right? If it's closer, it's even more attracted. If it hits the fridge, I have to put energy to remove it. And if I let it go, it goes to lower energy, like gravity pulls it in and it goes to a lower energy state. So when these things collide, they go to a lower energy state, right? That's all this formula is saying, that the energy is proportional to a constant times the charge, the bigger the charge, the bigger the energy. And distance on the bottom, because the bigger the distance, the smaller the energy, right? If I move it, if I separate it apart, there's less of an attraction, right? This formula is going to be used so many times this semester and beyond. I can't even tell you. In lab, we're going to use it. In lecture, we're going to use it. In the nucleophilic substitution chapter, we're going to use it. We're going to use it to describe things like hydrogen bonding and dispersion forces and so on. The nucleus is a positively charged center, right? And we're asking about the energy of an electron. Wouldn't the electron have the lowest energy if I put it on the nucleus? Just imagine the electron is a person and the nucleus is the Earth. Where is your lowest energy? Standing on Earth. And if I go to the top of a building and jump off, I'll fall towards my lowest energy, to my Earth, right? So over here, the electron would have the lowest energy, right? Then over here, the electron would have higher and higher and higher energy. It would kind of look like a curve like this. Yes? Now what if I change this from energy to possibility of finding the electron? Chance of locating an electron. Where would you have the greatest chance of locating an electron? Just look, think about this. You leave the room, and I put in the room, I'm here by myself, I put in a open shutter camera. Did you ever see those pictures with an open shutter camera? It's like cars moving on the highway, and you just see a streak of red lights because they open the shutter long enough so as the car's moving, the tail lights just streak out like that. Did you see these pictures? Imagine you put that kind of camera in here, and you leave it in here for an hour. You would see me, but spread, streaked out through the entire room, right? Now think about where most of my density would be. It wouldn't be up in the air. I would get bored and maybe hop around a little bit. But you'd see very little of my density over there. You'd see most of my density at low energy. If I was in here for hours, you'd see a whole lot of density in the... If I remove all chairs, all furniture, eventually I get tired and sit on the floor, maybe even lay down, right? Days, you'd see all my density on the floor. Lowest energy. Where would you find an electron if it's in this box that can only move back and forth on this line? Where would it be most of the time? It would be at the nucleus, where its lowest energy is. Of course, it could get bored and move away a little bit, right? So here is what the curve is going to look like. In the lowest energy place to find an electron. Now, you definitely heard something like this. If you put in, what is an atom, right? It's got a nucleus and it's got an electron. But remember, there was like this uncertainty principle, and from there, you would say you don't even have a perfect size of an atom. It's just where 90% chance to find an electron is. That's the atom. And there's always some small chance that the electron is beyond that space. Have you heard this before? If you haven't, you missed something in chapter 6. The chapter that was 1s2, 2s2, 2p6 in Gen Chem. Because the electron is a cloud of density, you can't say an atom is a fixed size. Because it's a cloud. It's just thicker here and gets thinner and thinner and thinner. At some point, it's sort of like our atmosphere. We say our atmosphere goes up 600 miles, but really there's some particles beyond there. It just gets so thin that beyond that we say, okay, we've got to get a cutoff somewhere. Point is, here's the nucleus, and to the left and to the right is sort of infinite distance, and there's progressively less and less and less chance of finding the electron, but there's never a zero chance. An electron in my finger can be found at the other end of the universe, but the chance of that is like 0.0, probably an infinite number of zeros than number 1. But there is some minute chance based on the uncertainty principle. So that is the chance of finding the electron in the lowest place. The chance of finding an electron, it turns out, in the next lowest place, next lowest energy, because this is actually the lowest energy map of an electron. There is the next level lowest energy map of an electron, and it looks like this. Why? What the hell is that about? Because what you are seeing over here is called a wave function. Do you see it looks like a wave? This is called a wave function. We can call this psi 1. Ever seen that symbol for the term wave function before? Call that psi 1. And all it is basically half a wave. Well, if half a wave is the smallest energy place, what is the next smallest? A full wave. And what's the next smallest? A wave and a half, let's say. And then 2 waves, and then 2.5, then 3 waves. It increases just number of waves. Must seem bizarre. Psi 2. Here's how the lesson is going to go. Because I understand, I know what it's feeling like from your side. So I said that electrons have wave-like properties, and I'm just drawing random waves. Well, we described the fact that an electron is in its lowest energy state when it's touching the nucleus. So at the nucleus, you have the largest chance, because the y-axis is chance, to find an electron. As you go away from the nucleus, you get less and less of a chance to find the electron. And if you graph that, it's the highest point at the nucleus. I'm not saying the electron is tall here. I'm just saying you'll find it most of the time there. And less of a chance as you move away. And if you graph that, the function looks like a wave. Strangely enough, that's the lowest chance, that's at the lowest energy spot. You go to the next higher energy spot and you get this kind of a wave format. This is not going to make any sense until we then go and discuss orbitals and bonding, and then you're going to see they actually are behaving like waves, and these waves I'm drawing really mean something. So we have to give it a little time. Because this is half a wave, it could actually be a half a wave upward, or it could be a half a wave downward. That's going to make little sense right now, but this, since it's a full wave, you could see it maybe here. This is saying that the maximum chance to find an electron is some distance to the left of the nucleus, right? Or before some distance here. But what is the interpretation of this side? The interpretation of this side is what? If there's a negative chance of finding the electron? It's not. It's actually the way that waves go. So what physicists and chemists did was they said, we have to normalize this. These functions themselves are problematic in terms of interpretation, what the trough of this wave looks like. To normalize this, we'll take each of these functions. This again, by the way, is a nucleus. We'll take each of these functions and square them. Psi1 squared. We'll take this and we'll square it, psi2 squared. And the square of the wave function is known as the probability density. Have you heard of this term before, probability density? It was in Chem 1. Raise your hand if you've heard of the term. It's like one or two people. That's bizarre. This is something that has been repeated several times. Look it up. Look it up. Go into your Gen Chem book. Make sure you're not like totally ignorant of this. Spend 10 minutes looking it up. Not even a big deal. What happens mathematically when I square this? Well, look. Over here is a big number. You know, look, I need your attention. Over here is a big number. When you square it, it becomes bigger. Over here is a small number. When you square a small number, it becomes smaller. So it just looks more of this kind of like a bell curve kind of a thing. What about here? This is the more important part. This is the more important part. On the left side here, there is a big number. When you square it, it becomes bigger, right? So basically this ends up looking like what happened there with the square, except this side touches a 0, so a 0 squared is an actual 0. There's an actual 0 here. So it goes up and then it tapers off. It horizontally asymptotes. But on the right side, that's the whole point of normalization. When you take a negative number and you square it, it becomes a positive number. So the right side now becomes a reflection of that, and it looks like this. It goes kind of like that, but much closer, tapers off much closer, right? And this shows us what? What does this actually show us? The probability density. This kind of has to do with a energy position function, but this really shows us the probability, the true chance of finding the electron. And here, in the lowest energy spot that you're going to find in an atom, the electron has the biggest chance, because again, on the y-axis, look, going across this curve, where's the tallest part? The tallest part is right here. And that means it's the biggest chance to find an electron in the x direction. The position is at the nucleus. This is saying the biggest chance to find an electron is at the nucleus. And when we go over here to the next energy spot, the biggest chance to find an electron is not at the nucleus. There's actually a 0 chance of finding the electron at the nucleus here. Do you see it hits a real 0? Where is the biggest chance of finding an electron? Some distance to the left of the nucleus or some distance to the right of the nucleus is the biggest chance to find an electron. Could you see that? What does this mean? Now let me draw it in three-dimensional space. I'm going to take this one-dimensional picture and draw it up here in 3 dimensions. You guys definitely have to look in your Gen Chem book to see this again in the chapter with orbitals. The one, remember the one with the de Broglie equation? The chapter begins with like a line spectrum, and it shows you all the different colors, and it shows you like wavelengths, and then it says, you know, speed of light is frequency times wavelength, and then all of that, and gets the de Broglie and the Rydberg equation and all of this, right? Line spectra and so on. In that chapter, it has this. It has this actual discussion, except this is in one of those chemical connection boxes. By the way, here's how I was as a student. For all of you in the future listening and all of you listening now. Before I was a good student, I'd open the book and I'd say, I'm going to be a good student today. I'm going to read everything. You open up the chapter, after 5 words, you're like, organic chemistry is the study of, and you're like, ugh, how many more pages? And then you start flipping and counting pages. At least I did. And when you get to a page where they show you a picture, you're like, oh, thank God, I only need to read this portion. And then when you get to a page that says chemical connection box, you're like, I don't need to read this at all. And you're like super happy. Those are the most important things to read. Those chemical connection box make everything make sense in the chapter. When you read that, you understand what's actually going on. Then you read the chapter, you're like, that's why that happens. It's the magic. It's the magic. If you understand my lessons, it's not because I'm just throwing math at you. It's because I'm connecting it to other things. That's when you understand it. Read the chemical connection. Go back into this chapter. See this again. It's going to be confusing. In that chapter, I've had students that remember this, actually, when I taught Orgo 1, and they raised their hand and they said, but I saw in that chapter a different function that didn't look like this. It was called, I don't remember what it was called. I was like, it was a radial probability density. We'll deal with that in biochem. You don't need to know that far, but you need to know these basics. I'm going to now draw this 3-dimensionally. What this is saying is that there is a nucleus, and the biggest chance of finding the electron is right at the nucleus. And as you go away in any direction, you get less and less and less of a chance to find the electron. And since we call this probability density, I'm going to draw it like with marker, really dense when there's a lot of chance to find an electron, and thinner and thinner and thinner where there's less chance to find an electron. So the greatest chance to find electrons right here on the nucleus, and as we go away, we get thinner and thinner and less of a chance to find an electron. And if we circle what 95%, 90 to 95% of the density is to find an electron here, you're going to notice that this thing is a sphere. Yeah, there's some chance outside of that, but really it's a spherical shape. Do you see that? Now, if we go over here and try to do the same thing, we're going to say there's a nucleus. Now, where's the chance to find the electron? The biggest chance is some distance to one side of the electron and some distance to the other side, but equal distance. So the biggest chance might be here and here. And as you go away from that major chance of finding the electron, it gets thinner and thinner, less and less of a chance. So here's the major chance, and then it gets thinner and thinner. Here's the major chance, and it gets thinner and thinner. And if I circle 90 to 95% of where you could find the electron, it's going to look like this. So the lowest energy spot to find an electron has a spherical shape, and it's known as an s orbital. And the next lowest energy, but it's not the lowest, it's higher in energy, has a 2-lobe, double teardrop type of a shape that's known as a p orbital. You're going to see this on exams again, which is why I spent these minutes covering where this comes from. I could have just said, these things are wave functions. And because these things are called wave functions that turn into orbitals, orbitals are waves. And orbitals have wave-like properties. So what? Where do we go from here? Well, if orbitals are waves and orbitals have wave-like properties, we have to look in physics and see what waves are capable of doing, and then we could understand what orbitals will therefore do. Fair? So, if a wave, like a sine wave, is propagating. Everyone know that's a sine wave? Sine waves start at 0, go to a maximum, go to a minimum, go back to 0. If a sine wave is propagating and collides with another wave, there's so many ways that it could collide, but here's the major ways that it could collide. This one could be propagating like a positive sine wave, and another wave, let me actually draw this a little higher, and another wave could be propagating also like a sine wave, and they could collide into each other. And when they collide into each other, this kind of a process is called constructive interference. And if we just notice this, that them colliding, these waves colliding into each other, is really you're just adding these waves, right? So over here, sine of the sine of x or whatever, this is 0, this is 0, right? Over here, there is a maximum, let's say that's a 1, and over here is a maximum of 1, and 1 plus 1 is 2. So that means where you have that maximum, it gets bigger. Then it goes back to 0. Both of them go back to 0. Then over here is like a negative 1, and a negative 1 is negative 2. So the point is they constructively interfere when the two waves are propagating together. Waves are moving together. They collide. They make one bigger wave. Constructive interference. On the other hand, you could have this. You could have one wave moving as a sine wave, and the other wave could be moving the other way. Kind of wrote it in the wrong place. Like I said, I was a little distracted. This is where, when they combine this way, this is called constructive interference. And what you call two waves moving with each other is that the waves are in phase. These are perfectly in phase. To combat that, the opposite of waves moving perfectly in phase would be waves moving perfectly out of phase. Out of phase. What does that mean? Well, if one is moving like a perfect sine wave, then the other one will be moving like a negative sine wave. Now, these are not the only two ways that waves could combine. They don't have to be perfectly in phase or perfectly out of phase. They could be anything in between, right? So this is saying that the wave is lined up with the other wave either 180 degrees away or lined up perfectly 0 degrees. But one could be lined up with another 4 degrees or 7 degrees or 12 degrees. I'm just showing you the extremes. When they're perfectly out of phase, if you add these up, what do you get? Could you guess? What happens when you have a plus 1 and a minus 1? You get a 0. What happens when you have a minus 1 and a plus 1? You get a 0. This is called destructive interference. Well, orbitals do this. Orbitals are waves, and when they combine, they either combine in phase constructively, and when they do that, you call this bonding, or they can combine this way, destructively. Anyone know what you call this? You call it anti-bonding. Ever heard that term? Anti-bonding orbitals? Bonding orbitals? It comes from this background. Years ago, I taught Orgo 1 and never mentioned any of this. It's like whatever. And I just saw how like later in the semester in an Orgo 2, there was just some kind of nagging confusion. It's not like you're going to get answers right because you know this. You're just going to be more comfortable with the topics because and that comfort, the confidence in there is everything. If you get to Orgo 2 but have this feeling like you never learned Chem 1, you're never going to be confident enough to keep studying Orgo 2 the right way. You have to know the background so that you don't feel like you're missing some bit of information somewhere. Ever feel like that? Like you're trying to do a problem, you're like, what the hell do I need to study to know what I'm doing here? I felt that way a lot. So, now how do we actually process this in terms of chemistry? How do we actually put this together? Let's say you have a hydrogen atom. Why is that a hydrogen atom? Because what's the Lewis structure for a hydrogen? Hydrogen has one electron. That's it. So here's my Lewis, here's my hydrogen with one electron. Let's say a hydrogen atom is in the universe and it meets another hydrogen atom. You know that that's not how hydrogen is in our... We might have some hydrogen molecules in this room. You know that's not what they look like. They look like this. It's not an octet rule that they're completing, but they need to complete their rows rule, and their rows rule is a duet rule. Because the first row has an s orbital, we've said, that could hold 2 electrons. Right? So here it doesn't have 2, it doesn't have 2, but when they share, they have 2. So if you had 2 hydrogen atoms and you let them go, they would collide and become one and become more stable and release energy. So you would have this plus heat. They would release heat. What would happen if I heated up hydrogen 2, H2 like this? If I heated it up enough, you could send this reaction in the other direction. So this is sort of an equilibrium. Now I'm going to start saying some things that are going to be kind of uncomfortable for probably everybody in the room. Because here's a topic from Gen Chem that nobody was ever really great on. It's so important for biology. It's so important for biochemistry. Anybody took a biology class before? Have you heard the term endergonic, exergonic in biology? When you get to biochem, every single thing we discuss is in terms of delta G. Now, of course, you've seen the equation. Delta G is delta H minus T delta S. But that doesn't mean you're truly comfortable with this. And it doesn't mean you could easily look at a chemical equation like that and analyze it and tell me what's going on in terms of delta H and delta S perspective. But we have to get started on this somewhere. And we will become experts. Maybe not by the end of this semester, but definitely by the end of next semester, as long as I keep giving you this equation and making you analyze every reaction through this equation. In the beginning, I'm telling you, it's not going to feel comfortable. Just get used to it, because later, not only will feel comfortable, it'll be the reason you remember things, because you understand their background. You all know, I hope, you know, that for a process to occur, delta G has to be negative. Saying that delta G negative is like me using the English words, it happens. I know in the chem book it says spontaneous, but spontaneous means it happens by itself without somebody else making it happen. So what's the point? If I let go of this marker, what is delta G for it to turn into a bird? You're going to say that doesn't happen. So that means delta G is positive infinity, because that doesn't happen. Because saying delta G is negative is just another term, you know what I mean? Like, imagine I said from now on, I don't want to use the words it happens. I want to invent a new word. Plip-plop. Right? So that's it. From now on I say plip-plop, and you know that means, oh, it happens. I'm sending you a problem set, plip-plop. It means you're going to get a problem set, right? Okay. Let go of this marker. It falls to the floor. True or false? Yes, right? So what do you expect delta G to be for me to let go of the marker and it to fall? The answer is negative infinity, or as close to negative infinity as possible. Is there any chance that I let go of the marker and it doesn't fall? Hurricane comes in and blows it to the side, right? Notwithstanding, delta G is negative, right? So for a process to occur, delta G has to be negative. Mathematically speaking, there's 2 different ways that delta G can be negative. If you look at this equation, delta H can be negative, and that is the way that delta G can be negative. Because look, if I erase this term, do you see delta G is equal directly to delta H? So if delta H is negative in a process, that would make delta G negative in a process. if I cover up this term, what kind of sign of delta S should we need for delta G to be negative? There's a negative in front of this already, so the kind of delta S we want would be positive, and that would make delta G negative. Now I could say, look, there's some process where delta H is negative. If that's true, you wouldn't really know what delta S is. But if I said, look, there's a process where delta H is positive, you would now know what delta S is. Little confused? Raise your hand if you're a little confused with what I just said. Totally fine. Totally fine. You're not? You perfectly understand? Let me use some English terms here. You know this is enthalpy and this is entropy. Forget those words. How about I say that the reason anything happens is for really two things. One of them, delta H, is stability. And delta S is actually freedom. And that's why we do anything. That's why humans do things. You want to be stable and free, right? Imagine I say, you took a job, and that job made you less stable. Do you think that would be a good reason you want to be less stable? What kind of stable do you want? You want to be less stable or more stable? You want to be more stable. You want to be less free or more free? More free, right? If I said, Joe took a job, and he became less stable, I guess you would say it's because he got more free. Right? One of the two reasons, right? If I said Joe took a job and became less free, you'd say, he must have become more stable. If I said Joe took a job and became more stable, you wouldn't know if he became more or less free because the thing that I mentioned is good, so the other one could be good or bad, right? I could even turn it into an easier thing. You take an actual job either for money or because you love the work. And I said, Joe took a job and he's making millions of dollars. Does he like the work? You're like, I don't know. Joe took a job, he's making no money at all, but he's going there every day. Well, I guess he must love what he's doing, right? Do you understand what I'm saying? The freedom part sometimes is easy to notice. Think of this as a marriage. You lose your freedom if you get married. Two things join and become one, they lose their freedom. In a chemical reaction, entropy increases in a direction if one thing breaks up into more things. Freedom increases when one thing breaks up into more things. Think of the Big Bang. That was the biggest entropy increase ever. One thing broke up into the whole universe. And if the whole universe compresses into one thing, it lost all its freedom. And by the way, why do you get married? People get, besides love, let's say contractual from feudal society, right? People got married so that this king's plot of land and that king's plot of land became bigger, they became more stable. Just the individual parties lost their freedom. Why'd they get divorced? Screw stability, I want my freedom. Right? Do you see that? If you have an equilibrium, now this is what puts it all together. If you have an equilibrium, that means the reaction happens this way for a reason, and it happens that way for a reason. Meaning, it can't be that going this way is both better in stability and better in freedom, because then there'll be no reason for it to ever go the other way. It can't be that this way is for enthalpy and entropy, because there'll be no reason for it to go that way. Heat is not a thing, it's just energy. Do you see on the left side of the equation there's two things? And on the right side there's just one? They got married. Going from these two to one, they got married. Going this way, they lost entropy. Do you see going this way, they broke up and got more entropy? Do you see that? So in this direction, delta S increases. That's the reason it goes this way. Tell me about the reason it goes this way. Look, let's say this again. If delta S increases this way, doesn't delta S decrease this way? So that means that's bad freedom. If the reaction goes this way and it's not for freedom, why is it? Stability, right? And of course, if it's delta H negative, that's why it's releasing heat. Do you see? Because delta H is negative, exothermic, releasing heat. So this way is for entropy. This way, is for enthalpy, delta H negative. Do you know that we could control which way it goes? What can we do to make a reaction go towards stability or towards freedom? There's one variable that we could control. The answer is temperature. If we add temperature, you multiply the importance of the freedom because temperature multiplies freedom. If you add temperature, you make it go in the entropy direction. If you cool it down, you make it go in the other direction. Because if you bring this to 0, 0 times anything is 0, and the enthalpy will govern which way it goes. See, look, when you heat this reaction, remember Le Chatelier's principle? I add heat and it goes this way and removes the heat. When I heat it, it's not going this way because endothermic. Endothermic's not a reason for a reaction to happen. Exothermic helps delta G become negative. Endothermic makes delta G positive. So what's the reason that it would happen? You would say, even though it's endothermic, it still will happen because of entropy. Do you see what I'm saying? Again, you could take a job because you love the work or because you're making money. And if you said, oh, I took the job and I hate the work, that's not the reason you took the job. You took it despite hating the work. I must be making extra money. I feel like, with the level of attention everyone has in the room, that you basically got most of the elements that I'm trying to explain about this. It's just we're going to have to see it in many different reactions and make sense out of it. But how does this connect? How does this connect to orbitals and so on? A hydrogen atom, which I will draw right here, on an energy diagram, on an orbital energy diagram, molecular orbital energy diagram, a hydrogen atom has an orbital. What kind of orbital? Has an s orbital, right? Hydrogen atom has an s orbital. We'll call this the 1s orbital. And there is one electron in it. Right? Now next to that, make sure it's not too close. Give it some distance because we're going to put something in the middle. Some distance away, there's another hydrogen atom. And if it's another hydrogen atom, it's going to be the exact same energy because it's got the same 1s orbital. Do you see that? Now what is an orbital? An orbital is a wave. So we've got a wave right here, and we've got a wave right here, and these two waves are approaching. What are the two waves waves can approach? They can approach constructively, and they can add. Now an electron likes to live in an orbital. And if you give an electron a bigger, better orbital, it's going to be in the lower energy spot. It'll feel more comfortable. Imagine I changed your house, wherever you live, to like a 60,000 square foot Microsoft billionaire house mansion. You'd feel really relaxed. Right? If these two combine constructively, they're going to both go to a lower energy spot. But if they combine destructively, then you've killed the wave that an electron can be in. It's got no space to be. It's going to go to a much higher energy spot. And this right here is where the H2 molecule would be. We call this right here an atomic orbital, because this is the orbital of an atom. You call this an atomic orbital, because this is the orbital of an atom. And you call the combination of those orbitals, whether it's constructive or destructive, you call that molecular orbitals. These are molecular orbitals. Make sense? What is true about combining orbitals is, no matter if you're doing hybrid orbitals or if you're doing molecular orbitals, the number of orbitals you start with is going to equal to the number of orbitals you end with. Do you see I started with 2 atomic orbitals, and that gave me 2 molecular orbitals? It'll always be that when you combine orbitals, when they combine in a good way, constructive way, they'll go to lower energy, and when they combine in a bad way, destructive way, they'll go to a higher energy. Right? If there's an electron here, the way you really look at this picture is, this stuff right here, left and right, is before, and in the middle is after. So there was an electron here in this orbital, and there was an electron here in this orbital, and now they have 2 electrons. Now you ignore this, and you just think about the middle. There's 2 orbital levels, and there's 2 electrons. Do you remember Hund's rule and the Aufbau principle in how to fill up electrons? Let me remind you, just not to do with that. Do you remember if you had orbitals like this, like this, like this, and let's say we had 9 electrons. You would fill them up like 1, 2, 3, 4, 5, 6, 7, 8, 9. Do you remember that? You would put in a single electron in an orbital and check if any other orbital was degenerate, meaning any other orbital had the same energy. If it didn't, you would double up. But if there were orbitals that had the same energy, you would put 1 in each before you double up, right? We're going to do the same exact thing when we combine orbitals to make molecular orbitals in between. Ignore where these electrons were, just count how many of them there were. There's 1 here and 1 here. And when this combined to make a molecular orbital, in the middle here we have to put 2 electrons. 2 electrons. Well, there's the lower energy level, so I put 1. Now there's no other equal lower energy level, so I put 2. That's it. That's what I have. Remember, this down here is a bonding orbital, and we're going to call this a sigma bonding orbital. And this up here is an anti-bonding orbital. Remember constructive and destructive? Bonding, anti-bonding? This is an anti-bonding orbital. And the way we symbolize that is sigma star. If you ever see a superscript star, that stands for anti-bonding. That particular orbital is anti-bonding. So, turns out that the bond order can be determined, can be found in a molecular orbital diagram like this. What was bond order again? It was the number of bonds. The bond order between carbon and carbon right here is 1 because it's a single bond. The bond order between these 2 carbons is 2 because it's a double bond, right? Now I can't say the difference between this and this is bond length. There is a bond length difference. What I'm trying to say is I can't say the bond length of this is 1 and the bond length of that is 2. 2 what? Actually, let's ask the question. What's a longer bond? A double bond or a single bond? What's a shorter bond? Whichever way you want to answer it. Somebody raise their hand and tell me, what's a shorter bond? A double bond or a single bond? We didn't know that a single bond has a length and a double bond is shorter and a triple bond is shorter because it's bonded more. So wouldn't it be weird to say the length of this is 1 and the length of that is 2? 2 is bigger than 1, right? So, but that's the smaller length. You see how bizarre that is? This 2 is not a length here. 2 is the order. It's just, bond order just says how many bonds in that place, not how actual long in meters, right? You could find the bond order from a molecular orbital diagram in this way. The bond order is the number of electrons bonding minus the number of electrons anti-bonding. Divide all of that by 2. What is the bond order in the H2 molecule? What's the bond order? How many electrons are there bonding? 2 electrons bonding. Minus how many electrons anti-bonding? 0 electrons anti-bonding. Divide that by 2. What's the bond order? 1. Well, isn't there a single bond between H2? That's the bond order, 1. Now what happens? You all know this. What happens if I heat this up or put energy in so that the energy is exactly the size of this gap? What happens if a photon of energy flies like this? Let me draw it. What happens if a photon, let's call it h nu, a photon of light flies like that and hits that, and the energy of the photon equals the gap? Wouldn't that electron promote up to there? What would the bond order be then? you would have an electron down here, and then you would have one electron go to the top, and you would have an electron over there. What would the bond order be? What is the bond order now? You can't calculate it? It's 0. If you hit this with light, and it's the right energy, and that electron goes to the top, what is the bond order right now? It's 1 minus 1, which is 0 divided by 2. 0. What does it mean to have a 0 bond order? That there is no bond. How could that make sense? It makes sense right up there. If I put enough energy into this, I'll break the bond. How will I break the bond? By the electron going from the bonding to the anti-bonding orbital, canceling out the bond order, and now they just separate and walk their own ways. Does that make sense? That click? Why'd I call these sigma? Why? I know there's a bond, but why'd I call them sigma? Well, because it's a sigma bond, right? But how do you know what a sigma bond? What's the definition of a sigma bond? A single bond? But what's the definition of a pi bond? A double bond? That's not true. A connection of orbitals can be sigma, can be pi. They could even be delta. So what is the difference? A sigma bond, I've never written this as a definition on the board before. Let's see how it goes this semester. A sigma bond is a linear combination of orbitals where one lobe overlaps one lobe. A pi bond is a parallel combination of orbitals where two lobes overlap two lobes. Okay, let's make sense out of it. I've never written these words. I just showed pictures. It may be better if I put the words then with pictures. Here is an s orbital. This is a p orbital. Now let's say I combine two s orbitals like I did over there. Combine two s orbitals. Let's say here is the line. An s orbital approaches another s orbital. Do you see when they collide into each other, it's one piece combining with one piece? You're not going to see what I mean by lobe until I show the same thing happening with p orbitals. You're going to have a sigma bond out of p orbitals. What if I have a p orbital, but on the line it looks like this? It's like with the line. It's moving with the line. Because I could have drawn it turned this way, not with the line. But you see I turned it onto the line? What if you have a p orbital approaching another p orbital? Like this. Do you see this portion that I'm going to just point an arrow at? Do you see that portion? That's a lobe. That's one of two lobes. That's a lobe. And here's a lobe. And when they combine, this circle will overlap this circle, right? One lobe combining with one lobe. Well, what's the distinction for a pi bond? What if the p orbitals are turned this way? Do you see it's not along the line, but it's turned this way, perpendicular to the line? And imagine I have another p orbital like this, and these approach each other. What will overlap? The bottom lobe will overlap, and the top lobe will overlap. It'll be two lobes overlapping two lobes, and not one lobe overlapping one lobe. Do you see this? You can't get a pi bond out of an s orbital no matter what. You could get a sigma bond out of an s and an s. You could get a sigma out of an s and a p, because let's say you have a p orbital approaching an s orbital. It's possible they overlap and you get a sigma bond. The problem is you can't make a pi bond out of an s orbital because the s orbital is only one lobe. It'll never be a two-lobe thing to overlap with something else. There's other bonds as well. There's delta, and there's phi, sigma, S, pi, P, delta, D, phi, F, S, P, D, F. I'm not going to draw their definition. I'm just going to point something out on how these orbital shapes look before we continue on this mission. An s orbital looks like this, sphere, right? A p orbital looks like a teardrop, but I'm going to draw it kind of weird wrong. This is an s orbital. A p orbital is two circles. Right? That's not how we draw it. We draw it like this. But what if I draw two circles? It looks like an s orbital doubles and you get p. Did you ever see a d orbital? There is one that looks weird. It looks like a d orbital, one of them, the dz squared, looks like a p orbital with a donut running around there. I know you've seen that somewhere, maybe in a book. But all the other d orbitals look like four-leaf clovers. So if s orbital is one lobe, a p orbital double that, a d orbital is four, so it's a p orbital doubled. A d orbital is a p orbital doubled. What's an f orbital? Take this, double it, you get a p. Take this, double it, you get a d. Take this, double it, you get an f, right? So can you imagine 8 lobes? 4 in the front and 4 in the back like that? Rough to draw, but I'll try. Here's a f orbital with 2 more in the back that way and 2 more in the back that way. It looks crazy, right? But 4 in the front and exactly symmetrically 4 in the back. Do you see? Okay. So I can make, this is going to look complicated. I'm just going to probably stop at D. I can make a sigma bond between a D and a P or a D and an S. I can even make a sigma bond between a D and another D. Here's me making a sigma bond between a D and another D. There's one D. And here's another D. Do you see, because a sigma bond is one lobe touching one lobe. Do you see one of the lobes of D is touching one of the lobes of D? That's a sigma bond. I can make a pi bond. How do you make a pi bond out of a D and another D? I would need 2 lobes touching 2 lobes. That would look like this. Do you see 2 lobes touching 2 lobes? If 1 and 1 is a sigma and 2 and 2 is a delta, is a pi, what's a delta? You see it keeps doubling? 1 and 1 is a sigma, 2 and 2 is a pi, what's a delta? That would be 4 and 4. All 4 touching all 4. Do you see if I take this d orbital and a different atom's d orbital and sandwich them, you'd have 4 lobes touching 4 lobes? It's going to be a little difficult to imagine a phi orbital with 8 lobes touching 8 lobes. But you could Google it and you could see what a phi orbital might be, and there's some strange cases where 8 lobes could actually touch 8 lobes. Do you see why I said this is a sigma? I know we went like a little far, but do you see why I said it's a sigma? Because if you have an S and an S, you can only make a sigma. There's nothing else that you could make. But we have some symbolism here that we need to use, and you're about to see why I showed you the orbital crap in the beginning. The thing is that a sigma orbital, which is this, actually comes from this wave function, but the wave function can be that. Remember that first simplest wave? The wave function can be that. Technically, it could also be this. Because a sigma, why am I saying sigma? The s orbital is a half of a wave. But as a half of a wave, it could be a half wave up or it could be a half wave down. Now, for many years, chemists were struggling on how to present this to students right and how to write it correctly on the board. It's like almost like a naming thing, right? So stay with me. At first, chemists said, because look, if 2 of these orbitals overlap each other, you're going to have constructive interference. If two of these orbitals overlap each other, you're going to have constructive interference. If one of these overlap one of these, you'll actually have destructive interference, anti-bond, right? So how do you show that on paper, right? Because we're drawing a circle. So what chemists first decided to do was say, okay, we'll just call this the positive one because it's up. We'll call this the negative one because it's down. We don't do this ever anymore. You will never see this in a book. Why? Because then teaching a class, teaching a lecture, this must have been hilarious like 60 years ago. Teaching a lecture, then a professor said, okay, so that means if we have the constructive interference, bonding, you would have to have two of the same kind of orbitals, and that would be bonding. Or you could have two of these kind of orbitals and be bonding. And you know, students only half pay attention. So obviously at this point somebody raised their hand and say, I thought negative and negative repel, and positive repel. And then the professor would have to say, they're not negative, they're not positive, we're not talking about ions. We're just talking about a wave up or a wave down. Do you see where the confusion could lie? So they had to abandon this. They had to completely abandon positive and negative. The next thing they decided to try to demonstrate that waves can be either one direction or another direction is let's shade something. We'll say that if we shade, that's one of these, one type. And if we don't shade, if we leave it blank, that's the other type. So what would a bonding be? If both of them are shaded, that would be bonding. If both of them are unshaded, that would be bonding. And if one of them was shaded and one of them was unshaded, that would be anti-bonding. This has stuck all the way through me going to college and even me teaching like up until 10 years ago. But I kind of like what newer books have done. So newer books have abandoned shading and unshading. Why? Because then students start asking, well, which one of these is the shaded one? And the answer is, I don't know which one is shaded one. Nobody knows which one is shaded one. It's just, if I, in my book, decide to call this shaded, then this is unshaded. Or if I decide to call this shaded, this is unshaded. It's just having you realize that shaded is one of these and unshaded is the other one. So two of the same type work and two of the same type work. And it doesn't matter if they're both like this, they'll be bonding, or both like this, it'll be bonding. What did the newer books do? Rather than shading and unshading, just color code them differently. So in our book, you'll notice that they color these orbitals either pink or blue. And two pinks work and two blues work, and a pink and a blue is an anti-bonding. Which one is up or down, pink or blue? The answer is you don't know. It's not the point of it. It's just, I could decide to call this any name and decide to call this any other name, and it's two of the same names, they work together, right? So, if I have to show a graphical representation of this, I would say that this is going to combine together to make a bigger orbital. You see they kind of fuse together, melt together? And these would combine together to make a bigger orbital also. I'm going to shade that. But these destroy themselves. And remember, the destructive interference gives you a zero result because one is up and one is down, and it gives you a zero. The way we demonstrate that is we draw a line, and we draw these trying to get away from each other as much as possible. I'm not trying to draw a butterfly or anything like that. I'm just trying to draw them, get the hell away from each other. This one is shaded. That one is unshaded. And what you call this line is a nodal plane. The word node, N-O-D-E, stands for no overlap kind of result, meaning like where there is a node, there is zero chance to find the electron. Zero chance. We saw this before, right? I hope you guys are still with me. I said in the beginning of this lesson, this is a tough lesson to get through because it's like a lot of abstract things, but you just need major concepts. Do you have in your head that electrons live in orbitals, and those orbitals are waves? And waves constructively or destructively interfere, and that is bonding and anti-bonding. And we're going to have to start drawing these pictures, but not just random draw. We have to kind of understand them a little bit. Remember the p orbital, the wave function for the p? The s orbital was half a wave. The p orbital was a full wave. Remember it looked like this? And when we squared it, it looked like this. It touched 0 over here. So over here, where it touches 0, that's a node. There's no node here or no node here because it doesn't touch 0. It just gradually gets closer and closer to 0, but never actually touches 0. So I'm showing you all of the cases of sigma bonding with two s orbitals, anti-bonding. This one is anti-bonding, and these are both bonding. And now we can show the sigma cases for p orbitals. If I have a p orbital that goes like this and another p orbital that goes like this, we have to shade it. See, remember the p orbital wave. One side is up and the other side is down, which means one side is different than the other side. They can't both be unshaded, they can't both be shaded. One is unshaded, the other shaded. So here are the cases. Imagine this p orbital has a shaded side right here. And imagine this p orbital has a shaded side in the same direction. This is going to produce an antibond. Does everybody see why? Because which lobe is going to touch which lobe? An unshaded lobe is going to touch a shaded lobe. That's an antibond. What that's going to look like is as follows. You're going to have a nodal plane, and it's going to look like this. Do you see why the sides, the lobes that touched each other, killed each other and shrank to nearly nothing? What if they approached each other like this? Same way, except this one was shaded on the left and this one was shaded on the right. Now what? What would this do? Bonding or anti-bonding? This would definitely be bonding because the unshaded lobes would bind. And look what it would look like. You know, we're never going to draw these result pictures. You might see them on the MCAT or something again. This is just to see in your mind right now how when it's bonding, it increases density and size and all that. And when it's anti-bonding, it shrinks and disappears. Right? Do you see if these two pieces bond, then the energy kind of goes in there. That's what grows, and the other pieces shrink. So this side shrinks, the middle grows. This is bonding. And then there's one more case of this. What if you had a shaded side right here and a shaded side right here that overlapped? It would also be bonding, right? Because all you need is the same types. It doesn't matter if it's a peak or a trough, as long as they're both troughs, both peaks. So this is how it looks. And that's also bonding. These are not all of the cases of s orbitals and p orbitals because these are all the cases of the same kind, ss or pp. We could also think of cases of s mixing a p. So you could have, let's say, what would you get if this approached that? That would be bonding, right? What would you get if this approach that? That would be anti-bonding, right? In this direction, if this touch that, that would be anti-bonding, right? Do you see that? How do we draw? This is the molecular orbital energy diagram for H2. How do we draw the molecular orbital energy diagram for helium-2? What that means is you start by putting helium right here and helium right here, drawing the orbitals of helium, and then combining them. How many orbitals does helium have? The answer is 1. How many orbitals do you have on the first row? It's the first row. What does it have? S. That's it. 1 orbital. S. Helium has 1 orbital. It's a 1s. The other helium has one orbital. It's a 1s. That's it. One orbital. It doesn't even matter how many electrons it has if you want to figure out how it combines. If you have an s, what could this s be? Let's do it graphically. This s can be either the shaded one or the unshaded one. This s can be either the shaded one or the unshaded one. If this was shaded and this was shaded, what would it do? It would bond. If this was unshaded and this was unshaded, it would bond. If this was shaded and this was unshaded, it would anti-bond. You see, those are the only combinations. Combinations for you would be anti-bonding or bonding. That can come down and bond, or it could go up and anti-bond. If you have an s orbital and another s orbital, what kind of bond is it going to be? Sigma, pi, what is it going to be? Sigma. It's only one lobe and a one lobe. The only kind of overlap could be sigma. And that means this would be sigma star. Helium-2 would look just like hydrogen-2. Except, what's the bond order? So we have to fill in how many electrons this has. If you're going to put this on an exam, you don't have to draw the shaded, unshaded thing. You don't have to draw this, but you have to draw everything else. How many electrons does helium have? 2. Hydrogen is 1, helium is 2. So we put helium, 2 electrons, helium, 2 electrons. So you now have 4 electrons in total in the helium-2 molecule. Okay, helium-2 molecule. How do you fill out 4 electrons? 1, 2, 3, 4. Does helium-2 exist? Why or why not? That's a simple question every one of you should answer right now. Does the molecule of helium-2 exist? First of all, what is helium? What's the name of that kind of element? Yeah, so helium, neon, argon, what are they? Noble gases. Do they react? Do they bond? Why doesn't helium-2 exist? It doesn't. Does it exist? No. Why not? Because what's the bond order? How many bonds do you have between 2 helium atoms here? 0. There's no bond order, so there's no bond, so they're not together ever. That makes sense? How about this? Does the helium-2 cation exist? How would you get that? Well, what that would mean to have a helium-2 cation, to have a helium-2 cation, is that one of the electrons have been removed. Where do you remove electrons from? You always remove outer electrons before you remove inner electrons. So if we remove an outer electron, does helium-2 cation exist? Not helium-2 plus, but helium-2 with a plus. I don't mean 2 plus, not a double positive charge. Does it exist? To see if it exists, you would have to have some sort of bond between them. Is there any amount of bond? What is the bond order? The answer is 1/2. Because it's 2 minus 1, that's 1, divided by 2. It's always divided by 2. It doesn't matter how many orbitals it is, just divided by 2. 2 minus 1, the answer is 1, and then divide that by 2, half. So there's half a bond. What's half a bond? It's more than nothing. There's some amount of bond. So the helium-2 cation does exist. They're going to grab onto each other if you rip away an electron. Otherwise, they're going to just be inert. They'll follow the ideal gas law. What is the ideal gas law? It follows the kinetic molecular theory, which means gases move in straight lines and only change direction when they hit walls of the container or hit each other. The size of the gas is impossibly negligible compared to the volume of the container. When gases collide, they collide at a physics elastic collision, because if they would collide in an inelastic collision, that means energy would be transferred between them, but they're supposed to not transfer energy between them and just bounce off each other. And the pressure in the container is from how many collisions they have with the wall. And you'll have more collisions with the wall if you're moving faster, so temperature is a measure of the average kinetic energy of the gas. Did you know that temperature is a measure of the average kinetic energy of the gas? How many of you can state the kinetic molecular theory like I just did? Nobody? Don't walk into an MCAT unless you could do what I just did. It's not that you're looking at somebody that could walk in and get a 525 on an MCAT. It's that I could walk in and get a good enough score on an MCAT just like anybody else who knows as much as me. And anybody who got a 520 on an MCAT basically knows what I know. I'm not trying to teach you some tricks. At the end of Orgo 1, I want you to know all of what I know for Orgo 1. I'm not a magician. I can't make you also know all of physics and all of calculus and everything else I know. That's for other classes that I teach. Although, if I could teach you everything I know by the end of this semester, I would do it. What about your business? You know, they have ever heard the saying, like, pharmaceutical companies are trying to keep you sick? Because instead of curing a disease, they just want to sell you medicine so that you keep buying medicine from them. That's the stupidest thing in the world, because if I was a pharmaceutical company and I had the cure for a disease, I would just charge $1 billion for that pill. Why would I want to keep working and have somebody keep paying? So anyway, if I could teach you everything I know in one day, I would just charge $1,000, $10,000, $50,000, $50,000 for everything I know. Put it in your head, go to med school. It doesn't work that way. We have to build it slowly. I didn't get this in one day. I got this over many, many years. But the advantage to being my student is that if you're Bruce Lee, you have to learn Bruce Lee's fighting over his whole lifetime. But if you're a Bruce Lee student, he could teach you most of what he knows in 5 years or something like that, right? It's like if it took me 20 years to learn this, it'll take you 2 years if I teach you an accelerated. You see what I'm saying? That's what you're looking for. We did hydrogen. We did helium. I hope we have enough time to do lithium. We do. We have 5 minutes. In our next lesson, to prepare you, in our next lesson, and I have some homework for you to do, we are going to do lithium, and then I just want you to think about, go into the textbook, into the general chemistry textbook specifically. It's not really shown in Orgo. Go into the book and then see how it's dealing with orbitals over here, because hydrogen, helium, they just have one orbital each, s and s. What orbitals does lithium have? What's lithium's electron configuration? Lithium is 1s2, 2s1. The electrons in lithium occupy the 1s orbital and the 2s orbital. What's different from that in carbon? Carbon's electron configuration is 1s2, 2s2, 2p2. Suddenly you have to introduce the p orbitals. So when you're going to draw the energy diagram for carbon, you're not going to just draw 1s. You're going to draw 1s, a 2s, and all the different 2p's. Remember there's 3 2p's? 2px, 2py, 2pz. So I want you to kind of see that before you come into the next lesson so that we can get through most of those examples quickly. Then do not homonuclear, but heteronuclear, meaning nitrogen and oxygen, not just nitrogen and nitrogen. And then from there, we can now connect that to resonance and hybridization and kind of finish this chapter. That's what we need to do as soon as possible. So you need to prepare yourself. It can't be like, oh, I didn't do the work. Let's do lithium. Can a lithium-2 compound exist? So that means there would be lithium over here, and there'd be lithium over here. Now, what does lithium have? It has a 1s orbital. Let me draw it to the left. I keep drawing it to the right, but I'm going to put dotted lines over here. So I'm going to draw it to the left, 1s. But over here, in the same height, I'm going to draw it to the right, 1s. Do you see that? Not only does lithium have a 1s, you see it has a 2s. See, we're not worried about how many electrons there are. We're just worried about that the orbital exists. A 1s orbital, 2s orbital. Did you know 2s is greater energy than a 1s? You're supposed to know that. 2s orbital. Over here is a 2s orbital. Now you combine orbitals. You combine orbitals, right? They're waves that combine constructively. However, the 2s is not going to combine with the 1s. They're not in the same place. The 1s is over here, the 2s is over here. They're not going to reach each other right. There was questions like that on exams last semester in Chem 2. For example, carbon and carbon can make a pi bond with each other, but carbon and silicon can't make a pi bond with each other. Now, why is that? Because to make a pi bond, carbon is going to use a 2p orbital, and another carbon will use a 2p orbital. The orbital's in the same space. But carbon to silicon, carbon is using a 2p orbital and silicon's using a 3p. It's just like they don't reach. It's not the right overlap. So these two have relatively the same energy. They could overlap with each other. These have relatively the same energy. They could overlap with each other. Two orbitals overlap with each other. They could do it in a bonding way or an anti-bonding way. These two orbitals overlap with each other. They could do it in a bonding way or they could do it in an anti-bonding way. Yes, it's interesting that the 2s orbital bonding is higher up than the 1s orbital anti-bonding. Right? Do you see that? That doesn't matter. Question. How many atomic orbitals am I working with here? Atomic orbitals. 4. This is an atom's orbitals, and this is an atom's orbitals. 1, 2, 3, 4. How many molecular orbitals should I be able to generate from 4 atomic orbitals? The answer is 4 molecular orbitals. And in the middle I have 1, 2, 3, 4. You see every set of equal-ish, they don't have to be exactly equal. One could be a little higher, one could be a little lower. Just there's a limit to how different they could be. They could be slightly different, and that's going to happen when you have like nitrogen and carbon rather than nitrogen and nitrogen. Difference of electronegativity. I could give you this hint right now before we leave. If you have carbon and carbon, their 1s orbital will be the same. But if you have carbon and oxygen, oxygen's more electronegative, the orbital will be closer to its nucleus. It'll be lower. Do you picture that? They'll still be able to overlap. Do you see any two orbitals that are kind of the same will give you a lower and an upper bonding and an anti-bonding? Since these are s orbitals, you call this sigma, and you call this sigma star. And this one you call sigma, and this one you call sigma star. But you're going to have to do a distinction between the bottom sigma and sigma star and the top sigma and sigma star. So you're going to call this one sigma 1s, sigma 1s star, sigma 2s, sigma 2s star. Now what? The way you fill this up with electrons is completely independent of how you fill this up, right? This is filled up the way the element is filled up. How many electrons in lithium? 3. So you go 1, 2, 3. You got to see this because students have been confused in the past. This is just an atom, so I ignore everything there and I just put 1, 2, 3. This is the same atom, so I go 1, 2, 3. Now don't get confused that since these orbitals combine, you have to combine 2 electrons. Ignore that. Count up all of the electrons and start from the bottom with Hund's rule and Aufbau principle. Meaning there's 3 here and 3 here. Now I ignore where they're placed and I start from here and place 6 electrons because 3 plus 3 is 6. Start from the bottom. 1, 2, 3, 4, 5, 6. Is there any bond in lithium 2? How many bonds are there between lithium and lithium in Li2? There's 1 bond. There's 1 bond. Because the bond order is the number of bonding, that's all of the ones without stars, that's these, 4 electrons, minus the anti-bonding, that's this, that's 2, divided by 2, that's 2 over 2, and that's 1 bond, right? Here's an interesting thing. You have to read the question, because on exams, read the question, because the professor might not say, draw the complete molecular orbital diagram. This you somewhat remember. Do you remember there was 2 ways to draw the electron distribution here? Do you remember you could have drawn the complete electron configuration, or you could have drawn with the noble gas core? Remember that? Well, this you could also draw complete the way that I drew. Or I could ignore the inside and only think about the valence. See, lithium is on row 2, so I could just ignore everything inside and just draw row 2. The point is, this is bonding and anti-bonding, it kind of cancels itself, and the only thing that's really reacting is the surface part, that the bonding over there. Do you notice that? It's like if they said, draw the molecular orbital diagram, you don't have to show a core. It could be enough to just draw this. Because this is what's going on in lithium in terms of valence electrons, right? Just be careful, don't just draw this automatically, said Militsky said, right? right? On the MCAT, you write, Metlitsky said, right? That doesn't, who knows? Maybe these videos blow up one day, and then if Metlitsky said it, it's okay, right? But do we have enough time? Do I have another 2 minutes? It's 2:03. I have exactly 2 minutes. You have to go to class right now? Okay, because the next thing I was going to show you is the p orbitals. I guess you could go home, do the homework, which is look at them and practice these. Just practice more of them. Like we did that, so you could practice BE, for example. And then you could practice mixing something like lithium and beryllium, or hydrogen and helium. And then try to think about how to do the 2p elements. And we'll deal with that when we come back. Thank you for your participation. Hit like and subscribe.